Welcome to The White Space, a podcast where we talk about data centers in a simple and practical way.
Welcome back to the deep dive. This is part of the White Space podcast, and honestly, I am absolutely buzzing today. This is our fourth deep dive, and we're tackling something huge, something fundamental, yet often totally unseen in enterprise data centers. We're talking about the electrical power system.
The invisible heartbeat, really.
Exactly. Our mission today is to understand how that electricity, that vital pulse, gets from the grid through all these layers of protection right to the servers, keeping our digital world alive. It's, foundational to everything here on White Space or Piece of Blanco.
It absolutely is. And when we say critical, we mean the most critical element. Forget the servers, the cooling. None of it works without reliable, clean power.
It powers everything. The IT gear, the cooling systems, all the support stuff.
Without it, you've just got a very, very expensive, quiet room.
And the cost reflects that, right? Our research shows electrical systems. They're the biggest single piece of data center improvements. We're talking, 40–45% the total development cost?
Easily. It's a massive investment. Nearly half the build cost often goes into just the electrical side.
Wow. So beyond that huge upfront cost, what about, the hidden costs if things aren't optimized or resilient?
That's where it gets really painful. An outage. It's not just lost processing time, it's reputation, it's potentially lost data, it's the huge scramble to recover.
Yeah.
And the number one cause of unplanned data center outages. It's uninterruptible power supply failure, the UPS system.
Okay.
And the estimated average cost for just one of those outages, get this, $740,357.
Wow, $740,000 for one incident.
Yep. That really drives home why getting this right isn't optional. It's business survival.
Okay, that number alone tells the story. This whole chain, grid to rack, needs incredible attention to detail. So for you listening, let's trace that path. We're going on an electrical journey today, starting right where the power hits the building, through all the protective layers, right down to the servers. It's going to be fascinating. But first, a huge thank you to our amazing sponsors, Cirrus Tech and Noxtel. Your support makes these deep dives possible.
Absolutely.
You can find links for them right there in the description. Okay, let's start the journey. Picture that power grid, like a huge river flowing towards the data center. Most enterprise places, they start with the familiar city power grid, right? The municipal supply.
That's the primary source, yes. Always on, generally reliable. But
There's always a bug.
there is. Relying only on the grid, that's a huge gamble for these critical sites. The grid, it has issues, little voltage dips, surges, harmonics, stuff that IT gear really hates.
Right, tiny fluctuations can cause big problems.
Exactly. And that's why you absolutely need backup generators, usually diesel, sometimes natural gas. These are the heroes waiting in the wings,
Ready to jump in if the grid fails or even just hiccups.
providing that crucial continuity, fail-safe power.
So we've got this raw power coming in, either grid or generator. But you can't just plug servers into that, can you? What's
Yeah.
the first step inside?
No, definitely not. The voltage is way too high. That's where transformers come in. They're the unsung heroes, really.
Okay.
They step down that high voltage from the utility or the generator feed, reducing it to the precise levels the data center equipment actually needs.
Like tuning it perfectly?
Exactly like tuning it. Get the voltage just right so nothing gets fried. Once that voltage is correct, the power makes its first big start inside at the main distribution boards, the MDBs.
MDBs, got it.
This is like the central station. Power gets directed from here to all the different systems across the facility. And working closely with that, you have switchgear. I like to call it the traffic cop of the power system.
Huh, I like that. Traffic cop.
It controls where the power goes, but crucially, it's about safety and isolation. If there's a fault somewhere, the switchgear can isolate that section.
Preventing a cascade failure. Keeping one problem from taking down everything.
Precisely. That's fundamental data center design. Now, for the bigger data centers, say over 1 megawatt of IT load,
Okay.
you'll typically see medium voltage switchgear, MV switchgear. That's where the utility power physically enters and where the generators connect in. It's the main gatekeeper. Uses breakers, fuses, meters to protect everything downstream.
And for smaller facilities.
Under a megawatt. Then you're usually looking at low voltage switchgear, LV switchgear, or maybe switchboards. They do a similar job but handle lower power levels, directing flow from the transformers or generators to the servers, the cooling, and so on.
Makes sense. Now, what about switching between sources? Like grid fails, generators start. How does that happen seamlessly?
That's the magic of the automatic transfer switches, the ATS. These are brilliant devices. The ATS monitors the incoming power. If the grid power dips or fails, bam, it automatically switches the load over to the backup generator feed.
Instantly.
Almost instantly. Fast enough that the critical systems don't even notice, especially with the next layer of protection we'll talk about. And in redundant systems, an ATS can switch between two different power paths too. It's all about zero interruption.
Zero interruption.
Yeah.
Okay, so power's tamed, it's directed, it can switch sources. What's the absolute frontline defense against even the slightest flicker?
Now we get to the heart of it for IT loads. The UPS systems, uninterruptible power supply.
Uninterruptible guardians. I love that term.
It fits. They are central to keeping that critical IT gear running through any power hiccup. Short outages, surges, sags. The UPS handles it.
And it buys time, right, for the generators.
Exactly. It provides that clean, battery-backed power immediately, giving those big generators maybe, a minute or so to start up and stabilize. That minute is critical. And understanding the types of UPS is key. Our sources point to 3 main configurations. Each handles power differently.
All right, let's break them down. What's the first type?
The gold standard really is online double conversion. Power is always flowing through it. It converts AC from the input to DC for the battery and inverter,
Okay.
and then converts it back to perfect AC for the output. This double conversion creates a flawless, stable power signal.
So it cleans up any grid noise, too.
Completely. Protects against pretty much any power disturbance. Ideal for big, critical enterprise data centers. And crucially, zero transfer time to battery if the input power fails. It's already running off the converted power.
Sounds perfect. Any downsides?
Well, that constant conversion, it generates a bit more heat and it's slightly less energy efficient than other types. So, that impacts your cooling load and your PUE, your power usage effectiveness, something to factor in.
Right. Efficiency matters. Okay, what's the next type?
Next up is line interactive UPS. This one also conditions power and provides battery backup. It's really good where you have frequent small fluctuations like sags or swells. It can adjust the output voltage without switching to battery for minor variations. When it does need to switch to battery, there's a tiny break, maybe 4 to 6 milliseconds.
Okay, very short. A good middle ground.
A very solid middle ground option, yeah. Balances protection and efficiency well for many uses.
And the third type?
That's the offline, sometimes called standby or battery backup UPS. This is the most basic and cost-effective.
How does it work?
Normally, power just passes straight through it from the input to the output. It only switches to battery power when the input power actually fails or drops too low.
And the transfer time?
A little longer here, maybe 6 to 8 milliseconds. Still very fast, but there is that brief interruption.
So probably not for the main IT load in a big enterprise data center.
Generally not for the core systems, no. Better suited for less critical things, maybe desktop computers or smaller network closets.
Got it. And inside all these UPS systems, batteries, the first responders.
Absolutely essential. They take that initial hit the second the power goes out, bridging the gap.
How long do they typically last? It seems like a tough job.
It is. And they don't last forever. Typically, you're looking at a 5 to 6 year useful life for standard data center batteries like VRLA, sometimes less depending on conditions.
5 to 6 years. That's shorter than a lot of other gear.
It often surprises people, and it means you have to stay on top of maintenance, semi-annual inspections, testing. That's crucial.
What are you looking for in those checks?
Things like low voltage readings, any signs of swelling on the battery casing, corrosion, persistent low battery alarms from the UPS. These are all warning signs. You want to catch a failing battery before it fails during an actual outage.
Makes sense. Proactive is key. Okay, let's move downstream. Power leaves the UPS. Where does it go next? Let's talk PDUs, power distribution units. This term causes confusion sometimes, right?
It really does, because PDU can mean a couple of different things, but broadly, yeah, PDUs take that protected power from the UPS and distribute it out to the IT racks and other loads, and they often monitor it too.
Okay, so what are the main types we need to differentiate?
2 main categories. First, you've got the large floor-mounted PDUs, sometimes called cabinet-based PDUs.
Right, the big boxes you see on the data center floor.
Exactly. They might be the size of a server rack or even bigger. They take a large power feed in, often directly from the UPS, maybe do some final voltage transformation, and then break it out into multiple smaller circuits to feed rows of racks.
Distributing power across the room.
Correct. Although, interestingly, some modern designs are actually replacing these big floor PDUs with more standard electrical distribution boards to save space and cost. It's an efficiency move.
Okay. So that's one type. What's the other common PDU?
The other type is what most people probably picture now, The rack PDU, or RPDU.
The ones inside the server racks, like fancy power strips.
Exactly like fancy power strips, usually mounted vertically along the side or back of the rack. They take power, often from the floor PDU or directly from an overhead busway, and provide the outlets for the servers, switches, storage, whatever's in that rack.
And these can be pretty sophisticated now, right? Not just basic outlets.
Oh, yeah. Many are smart or intelligent RPDUs. They connect to the network. They can monitor the overall power draw of the rack.
Okay.
Some can even monitor power at each individual outlet, plus environmental stuff like temperature and humidity sensors right there on the PDU.
Per outlet monitoring. That's useful.
Hugely. And some even let you remotely turn individual outlets on or off.
So if a port seems dead on an RPDU, it might not be broken.
Exactly. That's a great practical tip. Before you assume the RPDU is bad, check two things. One, is there a little circuit breaker on the RPDU itself that might have tripped?
Right.
Two, if it's a switched RPDU, could someone have remotely disabled that specific outlet through the management software? Happens more often than you'd think.
Good tip. And usually just plugging into another free outlet on the same RPDU is fine.
Perfectly fine, assuming the overall PDU isn't overloaded, which the monitoring should tell you.
Makes sense.
Yeah.
Now, how does power get to these PDUs, especially in a large space?
Good question. Two main ways power travels around the white space itself. You have busway systems. Think of them as modular, prefabricated electrical tracks, like Lego for power distribution. They often run overhead, sometimes under the floor.
Flexible.
Very flexible. You can easily tap into them wherever you need power for a rack or a row. Great for upgrades or changes later on. Minimizes downtime during work, too, which is huge in big data centers. Very common in the facilities we look at for the white space.
Okay. Busways. What's the alternative?
The alternative is traditional cabling, running individual conduits and wires from the distribution panels to the racks.
The old school way.
Pretty much. Still used, of course, but here's a picker. For critical power distribution, busway systems can be almost 60% more cost-effective than traditional cabling.
60%? Why?
Faster installation, less labor, more material efficiency. Plus, get this, busways can free up about 8% of valuable data center floor space.
How?
Because they often run overhead, feeding RPDUs directly, you might eliminate the need for those big floor-mounted PDUs entirely. More room for servers.
That's a massive advantage. Cost and space. Okay, down at the rack level again? Circuit breakers. We need them, obviously, but there's a specific concept that's crucial, right?
Yes, absolutely critical. It's called circuit breaker discrimination, or sometimes selectivity.
Discrimination. Explain that.
It means that if there's a fault, say a short circuit in a single server's power supply, the circuit breaker closest to that fault, usually the one on the RPDU, should trip first.
Okay, the local one trips.
Right, before any larger breakers further upstream, like the one feeding the whole row or the main breaker back at the panel.
So it contains the problem, it's just that one device or that one outlet.
Exactly. You don't want one faulty server tripping the breaker for an entire rack, or worse, a whole section of the data center. That would be a disaster.
So this needs careful design.
Has to be designed in from the start. It's not an accident. And it also means setting the trip characteristics of the breakers correctly during commissioning. They don't always come from the factory set up perfectly for data center loads. Needs verification.
Got it. So we've got all these components, pathways, protection. How does it all come together to guarantee uptime? To really design for no interruption?
That boils down to one word: redundancy.
Redundancy. Building in spares.
Precisely. Enterprise data centers simply cannot rely on a single power path, so they implement dual or redundant electrical circuits. Two independent paths feeding the critical equipment.
So if one path has maintenance or fails,
the other path takes the full load seamlessly. No interruption. This applies to everything critical.
like what specifically?
Backup generators, the UPS systems, the PDUs, the power feeds to the racks. You duplicate them. This leads to configurations like N+1 or 2N.
Okay, N+1 versus 2N. What's the difference?
N is the number of components you need to run the load. N+1 means you have N+1 extra identical component as a backup. If one fails, +1 takes over.
Makes sense. And 2N?
2N is full duplication. Two completely independent systems, A and B. Each system, N, can carry the entire load on its own. So you have two separate utility feeds, two sets of generators, two sets of UPS, two sets of PDUs, everything mirrored.
Maximum reliability.
Maximum reliability. It eliminates single points of failure entirely. But, as you can imagine,
Much higher cost to build.
significantly higher, so it's always a trade-off. How much uptime can you afford, essentially? It's a core decision in data center design, something we often discuss on the white space.
Okay, so we have the infrastructure, the redundancy.
Yeah.
How do we manage and optimize all this power?
Technology helps a lot here. We mentioned those smart or PDUs.
Right, the network-connected ones.
They're not just for basic distribution. They are key power management systems. They constantly monitor power usage, voltage, current, feeding that data back to central management tools.
So you get real-time visibility.
Exactly. You can see which racks are drawing the most power, identify trends, spot potential overloads, track efficiency. It allows for much smarter capacity planning and operational management.
Data-driven decisions.
Precisely. But all the smart tech in the world doesn't replace good old-fashioned maintenance.
Preventive maintenance, PM.
Absolutely essential. You can't just install this stuff and forget it.
Yep.
Regular scheduled PM is key to reliability. It's about preventing failures, not just fixing them after they happen.
How much difference does it really make?
A huge difference. Get this stat. Regularly maintained UPS systems have a MTBF mean time between failures that is more than 20 times better than systems that aren't maintained.
20 times. That's incredible.
It really underscores the value. We're talking about things like, remember the battery checks, semi-annually.
Yep.
Replacing capacitors in UPS systems maybe every 5 to 7 years. Checking fans are clean and running, inspecting connections for tightness, replacing air filters monthly to stop overheating.
All those small things add up.
They prevent big, expensive outages. It's that invisible work that keeps everything running smoothly.
And alongside reliability, there's the push for energy efficiency.
Always. It's not just environmental responsibility, though that's important. It's pure economics.
Lower power bills.
Exactly. Using high-efficiency transformers, modern UPS units that operate efficiently, even at partial loads, it all reduces operational expenditure, your OPEX. And it lowers the data center's carbon footprint. It's a major focus for modern facilities and definitely for us here at the Whitespace podcast.
And finally, tying this all together. Standards.
Absolutely crucial. Adhering to international and national standards like IEC, ANSI, the National Electrical Code, or NEC in the U.S. is non-negotiable.
Why?
These standards define best practices for safety, reliability, performance. They ensure everything is designed, installed, and operated to the highest benchmarks. Protects equipment, protects people, ensures interoperability. You just have to follow them.
Makes perfect sense. Okay, what a journey through the power infrastructure. So wrapping this deep dive up, it's crystal clear, isn't it? A robust, reliable, efficient electrical system is the absolute foundation of any modern enterprise data center.
Couldn't agree more. It guarantees that high availability, protects the data, keeps the digital world turning. It really is the backbone.
The unsung backbone of the whitespace world.
Exactly. And for you listening, our call to action is simple. Take a hard look at your own data center's electrical health. Are you doing the PM? Are you monitoring effectively?
Consider those proactive steps.
Mm-hmm.
Maybe partner with skilled service providers.
Because as we learned today, prevention pays off massively. Don't wait for that $740,000 outage to get serious about power.
So true. And here's a final thought to leave you with. Data centers are evolving incredibly fast. Think AI, think high-density computing.
Yeah.
The power demands are skyrocketing.
Oh, yeah.
So the provocative thought is, what surprising new power challenges are just around the corner? And how will these fundamental principles we've discussed today need to adapt and evolve in the coming years? The power story is definitely not finished.
Not by a long shot. It's going to be fascinating to watch.
Absolutely. Okay, a final massive thank you to our sponsors, Ceres Tech and Knoxtel. Please do check out their links in the description.
Thanks to them.
And thank you for joining us on this deep dive, part of the Whitespace podcast. We'll catch you on the next one.